In this video, I am going to explain about pipelining and various hazards occurring in pipelining. Pipelining is an implementation technique in which multiple instructions are overlapped and executed in one clock cycle to increase the speed of the processor. Multiple instructions are overlapped and executed to increase the speed of the processor. To explain this pipelining system, let us consider the laundry system in a hostel. For example, consider the laundry system consists of a washing machine, dryer. So once the clothes are dried, it is put on the table for folding. After folding, it is kept on the cupboard. For example, you consider 4 students are washing their clothes. So first student using this machine for washing. After completing washing, it is dried, folded and kept in the cupboard. So second student starts washing after 8 o'clock only. So the 4 students can complete this washing at 2 a.m. only. This is a non-pipelining activity. In this case of pipelining activity, here first student completed this washing of clothes in the washing machine. Now he is moving to dryer. So in that case, the washing machine is free. So the second student can utilize this washing machine for washing the clothes. And in this third cycle, first student is folding. So second student can use the dryer for drying the clothes, and the third student can use the washing machine. So by doing this, we can complete this work with 10 a.m. So by overlapping the process, we can reduce the time. This is the concept of pipelining. Multiple instructions are overlapped and executed in one clock cycle. To increase the speed of the processor, execution time is reduced. The same concept is applied in pipelining. Consider the instructions of the processor are executed in 5 stages. First one, instruction fetch, instruction decode, and execute the instruction or address calculation. Then memory access, the data is written to the memory. Then the data write back, the data is written to the register. So instructions are executed in 5 steps. To explain the pipelining concept, we can consider this instructions: load word, store word, add, subtract, and or set less than, branch on, equal instructions. So the time taken to execute this instruction: load word, so we need 800 picoseconds, and store word 700 picoseconds. And this or format instructions, additional and logical operations, will take 600 picoseconds, and branch or conditional instructions will take 500 picoseconds to complete the instructions. For example, you consider the load word instruction. 3 load word instructions are used. So each load word instruction will be executed in 800 picoseconds. The total time period will be 2400 picoseconds. This is the non-pipelining techniques. In this case of pipelining, so load word, first the instruction is fetched, then it is decoded. So while decoding the first instruction, second instruction is fetched. And in this third cycle, the first instruction is executed, second instruction is decoded, and third instruction is fetched. Okay, so in one clock cycle, 3 instructions are executed. So this is called pipelining. So this pipelining speeds up the entire process. So pipelining improves performance by increasing instruction throughput as opposed to decreasing the execution time of an individual instruction. But instruction throughput is the important metric because real programs execute billions of instructions. Next one is pipeline hazards. So there are situations in pipelining when the next instruction cannot execute in the following clock cycle. So these events are called hazards. There are three types of hazards: structural hazards, data hazards, control hazards. In case of structural hazard, if the instruction is not executed due to inefficiency of the hardware, then it is called as a structural hazards. It means that the hardware cannot support the combination of instruction that we want to execute in the same clock cycle. Second one, data hazards. If the data needed to execute a particular instruction is not available for that instruction, that is called as a data hazards. Example, consider the instructions add and subtraction. Here the data in register T1 and T0 are added and it is stored in the register S0. And to perform the subtraction, we need the data from S0 register. Here this instruction is executed and the result is available in the S0 register in 800 picoseconds time only. But while executing this subtraction instruction, we need the data at the 60 picosecond time period. So here the data is not available in the S0 register to perform this subtraction instruction. So this is called as a data hazard. Here the data is not available to execute this subtraction instruction. This is called data hazard. So to avoid this data hazards, two techniques are used. One is the forwarding technique. Forwarding means the data is not, result is not stored in the memory. So after the execution, the result is directly forwarded to the execution unit. So this is called forwarding. Otherwise, stalls or bubbles are initialized to avoid this data hazards. Bubbles means, so in this instruction decode period of the second cycle, a bubble or stall is initiated. Bubbles or stall means it makes the processor in a floating condition. The processor will be in the idle condition. It will not perform or execute any instructions. By uh, inserting bubbles or stalls, the instruction fetch of the next instruction is delayed. So by delaying this, we can get the data for the execution. So this will avoid the data hazards. And the third type, control hazard. This control hazards happens whenever branching or conditional instructions are executed. For example, here consider the three instructions: add, branch on equal, and or. Okay, so in the second instruction, branch on equal means if the content in S2 and S1 registers are equal, then the control of the program should be transferred to memory location 40. Otherwise, it should execute the next instruction. Here, to check this condition whether the content in these two registers are equal, to check that condition, it will take some time. But in the meanwhile, the next instruction is fetched and decoded. But while verifying this instruction, the two contents are same. So you have to shift the control to the 40th location. So the instruction in the 40th location is R, S7, S8, S9. That is, the content of S8 and S9 should be R and the result is stored in S7. So after this instruction, we have to fetch the R instruction. But here the load word instruction is fetched. So this is called control hazards. In this case of conditional instructions or branching instruction, instead of fetching the correct instruction, wrong instruction is fetched in the next clock cycle. So this is called control hazard. To avoid this control hazards, whenever branching equations is faced, immediately bubbles or stalls are initialized to make the processor in the ideal condition. So after getting the result for this branching on equal condition, the processor will fetch the next instruction. Thank you.